Alright, so today I'm going to be talking about neutron stars, and I need to know that. Alright, so I'm going to bring this closer because I actually need y'all to be able to see what I'm writing. So, of course, these stars, they start out with the normal hydrogen. They compress. This is where the fusion that I talked about in an earlier video. Fusion, helium fuses to helium, hydrogen fuses to helium, helium to, then this is how most stars are. It's just fusing helium, and then helium's one of the bigger stars. But then, this star gets bigger and bigger, and then all the helium's used up, so then it's a stronger star and more gets carbon. Then it goes to oxygen, and then it goes to silicon, and then it goes to iron. Now iron is a little harder, and it doesn't like to be condensed. So when we get to iron, the star dies. And because it has so much gravity that this is with massive stars. Smaller stars, when this happens, it just dies, and well, the star will die here, and different things can happen. They can die and go to a dwarf star, but we're gonna look at what happens when it dies and it looks beautiful, and it goes into a supernova, because that's definitely what supernovas look like. So the pressure of all the gravity on the iron makes it collapse into a massive supernova, and that is how a neutron star is formed. And it can form a neutron star or a black hole, but we're going to focus on the neutron star. So then, we have a neutron star. And what's neat about this is, we're going to go back a few steps. That process is actually called Neutron Degeneracy, because the neutrons, they go like, because they don't want to hit, but there's so much pressure in this star, in this massive body, that they go against what we thought was a law of physics, and they collide and cause that massive amount of pressure that it explodes. And before these stars are about 8 to 20 solar masses. So that means our sun, the mass of our sun, these are 8 to 20 times that mass. But how big are they? They're about 25 kilometers, which a kilometer is kind of close to a mile. It's a little smaller than a mile, so less than 25 miles across. That's smaller than a city. So something that is more massive as in mass, like grams, not big, something that is more massive than our sun, compacted into something smaller than a city. And that's called dense. And that's how you get these things that are so energetic. And on the energy, we have the magnetic field that they have, which it's going like shoo, 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 shoo. And like you see these drawings that are like that. And this magnetic field causes a lot of wacky things because it has such a strong magnetic field, but these are also spinning really fast. A star that may have been spinning like once every few weeks, once it goes to a neutron star, since it's so small, it can spin many times a second. So really fast, plus really strong magnetic field, it sends out massive amounts of energy. We're going to do energy like different color instead of the, it sends out these massive amounts of energy. And these that send out massive amounts of energy just out the edge, that's what are called pulsars. So if you ever hear they then talk about pulsars in the news. That's what they're talking about, is pulsars. So another really neat thing that can happen is neutron stars can orbit each other. They can just be orbiting each other. But with such a close orbit, their orbits may start to decay, and eventually they may crash into each other. And they gave this a neat name. When they do eventually crash into each other, it makes this massive, really cool looking explosion. Much cooler than my scribbles across. And it's called a kilnova explosion. Literally, kilnova. It's a supernova, but it killed stars, so it's a kilnova. Yeah. But many things can happen here. One, heavier elements are created. So this is what people think may have created the heavier elements in our universe. Because earlier, stars died after iron. Well, if we look at a periodic table, there are some elements that are much heavier than iron. But these collapsing neutron stars, all those neutrons in the neutron stars combine, and they spread out, and fusion happens in that explosion, allowing for much heavier elements like gold and platinum, uranium, all those much heavier elements. They just are there now, and that's really cool. But another not as fun thing, if you think it's not that fun, I mean, I think it's kind of fun, but my marker seems to have fallen, so the black hole is going to be blue now because my black marker disappeared. From that explosion, you can have a black hole because those two big things of mass go in, mass amount of energy, big amount of energy, let's take the right numbers, words, big mass in small area, now you have black hole. And that's one way you can create a black hole, which we'll talk more about black holes in my other video, because that's a whole nother topic. But that is kind of a way that something that can happen with neutron stars. But now, more specifics about the actual neutron stars. How much do you think a cubic centimeter of neutronium weighs? Mass of it. They call it neutronium. That's just neutron star stuff because that's not scientific enough, so they call it neutronium. 1 cubic centimeter. So about the size of a dice, which I don't have within reach, of course, but about the size of a dice is 400 million tons. That's a lot of mass for something about the size of a dice. 1 cubic centimeter. But not only that, something that dense is bound to have a lot of gravity. And it's about 1,000 billion times Earth's gravity. That's a lot of zeros. So 100, 1,000, something around there. Somewhere around there. That might be there. So I weigh 140 about. So of our neutron star, this would be how much I would weigh. I'm gonna stay away from neutron stars as I'm trying to lose weight. But yeah, 100 billion times Earth's gravity. That's a lot. So if you were to be near the surface of a neutron star, first of all, you would die. You would be smushed to about the size of a few atoms thick. That would suck. But these are not only high gravity, but high heat. The sun is about 6,000 degrees Celsius. Pretty freaking hot. Because, just a reminder, 100 degrees Celsius is boiling. So, out of 100 boiling calories. The sun is 6,000. Want to know what a neutron star is? It is 1 million degrees Celsius. That's hot. That's really hot. So, you would not only be smushed, you would be burnt to a crisp because it's so hot. The amount of energy that the neutron stars have from their magnetic field, the heat energy that it has, all from the pressure that is being made from the supernova, and then it being such a dense thing. But what actually is going on in this thing? Well, that is honestly not known, because if we can't get that close, or we vaporized or smushed to the size of atoms, no one really has gotten close enough to say, hey, what are you made of? So we have theories. And so, like, the inside, then we have outside, and then... So we have an atmos. Forgot how to spell there, so we're just going to pretend those squigglies are words. Then we have an iron crust. Neutron stars actually have a solid crust around their gas core. So the gas core is where other things may be going on. Further fusion is happening here. But this iron crust is what makes it so wacky. And the neat thing about this, and I can't recall all the exact layers, but you have like spread out things, and then they get more dense, and then they start getting longer and closer together, then more long and more close together, until eventually you have these long sheets of super dense neutrons. And what's really funny to me about this is the super dense iron being crushed that has a bunch of neutrons. So this is the neutronium stuff that is makes up the crust. But because of the way it looks, the scientists, as they here, they call it pasta. Nuclear pasta. Pasta. And the only one I remember, honestly, is the bottom one, lasagna. But this stuff is the most dense thing, to exist. And the gaseous area is the part that we are completely unknown to. But in this nuclear pasta area, there are tiny little things. But this, you may see stuff in the news or something if you look at science news about neutron stars having mountains. That's what these are. But what's really funny about them is they're a few millimeters thick. They're like very small, but they're still something unique in this what looked to be all completely different stuff. So, yeah, neutron stars, they go from big star being huge, die, to tiny star being way more powerful than anything else. And that's pretty much a basic understanding of neutron stars. I didn't even get into magnetar. We touched on pulsars, but magnetars I did not touch on because they're scary. Basically, that's their magnetic field is so strong that they're the most magnetic thing in the entire universe. And that can screw up a lot of things if they are tampered with. But yeah, I will soon get a video out on black holes, and yeah, because fun thing about black holes and why I was originally going to make them all in the same video, they both start at this same origin point of dying in a supernova. But yeah, we'll sneak peek into the next video.